It has been a while since I've posted anything. I've had some family things I've had to prepare for and worked some really long hours at work, and sometimes after a 14-hour day you come home and don't feel like doing anything. Hopefully that's understandable. But what I want to talk about today is Endstops. And when I did my series on my printer, if you saw that one, I used 3 different Endstops, and I gave a little bit of information about how I connected those, but I was asked if I could give more information because I could have given more details about how they worked and how they interfaced into the controller. So the magic of this is that once you understand what the RAMPS board is looking for, and once you understand how different sensors work, then you can use just about any kind of sensor as an end stop. Switch, optical sensor, capacitive, magnetic, it doesn't matter really if you understand the ins and outs of it. So I'm going to make a longer video, and if that's not your thing, I get it. This one's going to have more technical information, so it may be a little dry, but I'll try to make it at best useful, and maybe at worst, tolerable. We'll see. I will say that this is probably going to end up being a 2-parter because the amount of information that I'm going to have to give on this to make it understandable, at least to the level I want it to be understood, is probably going to be too long for a single video. So this will probably end up being a 2-part video. So anyway, just a heads up on that. So let's get started. I'm going to start off with a standard RAMPS board here. This is an Arduino RAMPS Mega 2560 with your RAMPS 1.4, pretty standard stuff. And what I want to try to show is this this header right here, this triple row of pins right here. And I've got one row this way and it's labeled plus, and then there's another row labeled minus, and another row labeled S. And these 6 pins here are my 6 end stops: X minus, X plus, Y minus, Y plus, Z minus, Z plus. So anytime you connect an end stop, you're going to use that set of pins right there. So what does the RAMPS board want to actually see for a valid end stop? So if I were to draw a representation of my end stop connections, I've got a plus, a minus, an S. S meaning switch or sensor or signal, whatever you want to call it. It just means this is the information being sent back to the controller to say that the end stop has been triggered. Minus is ground potential. I'm just going to refer to that as ground. And plus is plus 5 volts DC. If I wanted to connect an end stop to my controller, and I'm just going to call the whole RAMPS Arduino combo a controller at this point. So if I want to connect an end stop to my controller, all the controller really needs to see is that this signal pin changes states. And typically this is from a high state of 5 volts down to a low state of 0 volts when it's shorted to ground. Those are the 2 states that you can be in on this pin. It's a high of 5 volts or a low of 0 volts. That's really all the controller is looking for, is the state change to see if your end stop is triggered or not. Now, this is fairly easy to accomplish by adding a switch. Here's an example of a switch. It's a pretty standard industrial switch. They make lots of different kinds of switches. Doesn't matter. But I'm going to draw my schematic symbol for a switch like this. So I could very easily just connect a switch between those 2 pins, between the signal and ground pin, and when I close my switch, then that switch connects the 2 pins together and triggers the end stop. So now, to explain how that works, I'm going to have to back up a little bit to explain a little bit about electronics and electricity. It's not going to be a full college course of it. It's just to be pretty straightforward. Hopefully I can make it not too technical. If I were to take a 9-volt battery And I've got my plus side there and my minus side here. And I want to connect that to, let's just say a load of some kind. We'll say it's a light bulb. So here's the schematic symbol for a light bulb. So I have to have a complete circuit, meaning current has to flow, and look, I'm not going to go into conventional versus electron flow. I just want to make this simple for people to understand that may not have a lot of background. So current has to flow from my positive terminal to my load, through my load, and back around to the negative terminal. If I get that there's a difference between electron flow and conventional flow. Don't go there. So that is a complete circuit. If I don't have a complete circuit and my wire is broken somehow, I don't have any current flow. This is kind of critical to what I'm trying to teach here. So you have to have a complete circuit to have current flow. If you don't have any current flow, then you don't have any current flowing through your load and no voltage dropping across it. So what do I mean by a voltage drop? I'm going to draw a digital voltmeter, and I'm going to say that my plus terminal, well, you know what, actually let me change that. I'm going to make that my negative. I'm going to connect it to the negative side of my battery. We're going to call that ground. So that's my ground potential and how I'm going to reference all my other voltages. And my plus side to the plus side of the battery. So let's just say if I just connected my voltmeter to my 9-volt battery, I'm going to read 9 volts on my voltmeter. So that seems pretty standard. If I put a load back on there, put that light bulb back on there, and I'm still going to read 9 volts, or about 9 volts. It'll probably drop a little bit because of the current being pulled out of the battery. But I'm going to move my meter lead to this side. I'm going to read 0 volts. I'm basically reading a short between one side of the meter to the other. So it's actually going to show 0 volts there. Oh, yeah, let me draw that in. So if I were to open that circuit, so I don't have a complete circuit, I don't have any current flow, I'm going to read 9 volts. All right, this is also critical. So without current flow through my circuit, I'm not going to have any voltage drop across my load, so I'm still going to read my full 9 volts. And by way of example, I could draw this circuit with a whole bunch of different loads here. I'm going to have 3 light bulbs, and let's assume that they're all the same values, voltages, and resistance. I'm still going to read my full 9 volts there. I don't have current flow. I don't have any voltage drop across these loads. If I connected the circuit back up so I have current flow, now I could read my voltage drops across each one of these loads. In an ideal world, assuming that all my 3 loads are the same resistance, then I would drop 3 volts across each one of these, and my load or my voltage drops would equal my supply voltage. So I drop 3 volts and 3 volts across those two, that's 6 volts. If I move my meter lead up to my source, I'm going to read 9 volts. As long as current is flowing, I have voltage drops across my loads. If I don't have current flowing, I don't have voltage drop, and I'm going to read my full source voltage across that open, no matter how much that voltage is or how many loads I have. So this is important because when you are trying to get your state to change on your end stop connector, you are going to, well, let me draw this here. I've got a resistor, just a type of load. It's kind of like a light bulb, it's just a resistive element. And I've got a switch to control my circuit, and I'm going to connect my meter lead like that. So right now, with the switch not closed, I'm going to read my my full 9 volts across that switch. I have no current flowing, no voltage drop across my resistor. So if I decide to now close my switch, I'm going to now read my 0 volts. It's just a short across the switch. There's no voltage drop. I'm going to be 0 volts. So those are my 2 states that I'm looking for in my end stop. I'm looking for a high and a low. 9 volts there, 0 volts there. I'm changing from one level to another. If this was my end stop switch, I would just push on the switch and close that circuit. My end stop now says that my switch is triggered. I went from a high state to a low state. That's all the controller is really looking for. So that's really it in a nutshell. If you connect a switch to your end stop, that's all that's happening, is your signal is... Now, this is not, let me back up. This is not an accurate representation of what's happening on your end stop. So let me redraw this. That would be more accurate. So let's go back to my end stop connector with my plus at 5 volts and my minus pin at ground and my signal pin, and that just goes back to the controller. If I want to see a state change, and I put a switch right here like that, let me draw that in. So that's between signal and ground. If I connect a switch there, that will not always show a triggered end stop. So I'm going to connect my meter lead one side to the signal and put my ground on my meter over to my ground pin. I need what's called a pull-up resistor. And that was what the resistor was in the previous circuit, is it's pulling up that voltage to the full source voltage of 9 volts, or in this case 5 volts. They call it a pull-up resistor for that exact reason. So it's going to pull the signal up to a positive voltage. When I close my switch, I'm reading my ground potential. Pull-up resistor is still there, but it's only in play when you have it connected to the ground pin. So I really have a resistor internally connected to my 5 volts, and this is inside the controller. So to go from 5 volts to 0 volts, that resistor is already on in the controller. You can turn it on and off in firmware, whether you enable it or disable it. And if you have just a simple switch there, it probably will need the pull-up resistor enabled, because if it's not there, you're not really changing states from anything from ground to anything else. It's just not connected to anything. So if you don't have a high state on your pin to start with, when you close your switch to get to a low state, you have to have a high there in the first place. So that's why the resistor is there. You could add an external resistor, which I've done before I knew what I was doing. I was just getting started. You could add one here from 5 volts down to your signal. There's really no point to do that, because you can do it in firmware. It's already there, and there's no point in not using it, or at least I can't think of one anyway. That in a nutshell is why you need to, how you can connect a very simple switch to your end stop connector and make it work.
Well, YouTube is being a jerk about my video sizes, so I am going to split this into 2 parts, and so hopefully if this was interesting, go see the next part. Thanks.